I will also go through the next chapter, responses, system responses. Okay. Any questions about the transfer function and stuff? Don't know what you ask, right? Yes, my work is done. Have you ever thought that you would have done so much easier by selecting some humanistic kind of studies, literature, poetry, music? Yeah, what is fun out on that one? Okay. New table. Fresh start. Impulse response. Okay. Impulse response is actually a way to calculate the output. Why I have the Fourier transform from delta. No, I would actually not do Fourier transform. So impulse response. It's simply the system is described by its transfer function, right? If it's an LTI system, then we have a transfer function, and if we have the delta input, then the impulse response actually comes out. So the definition doesn't actually care what kind of system it is. It can be LTI or just any arbitrary system with a function inside. Impulse response is simply that. It just describes how the system reacts for the impulse. Okay, if we have a linear time invariant system, then actually the delta in, and we have the transfer function of the nth order polynomial transfer function, we get the impulse response out. And there is actually a these are related. So, oops, not that way. The transfer function of the system is the transform of impulse response. All right, so now there's a example of 4-point running average filter. Y of n equals that. We just have the delta input, which means for simple 4-point running average filter, impulse response has 1/4 of delta at 0, 1/4 of delta at n-1. So the impulse response of 4-point running average system looks like that. Discrete sequence. The impulse response also, okay, let's see. Yeah. Describes if the system is finite or infinite impulse response. Simply FIR for the FIR, this is finite, meaning that after some place, for example here, this running average, is a finite impulse response system. It stops there, and there's absolutely nothing after that one. So after any point, meaning practically after the nth delay, there's nothing. So you don't need to check every single point after this nth order system. You just have to take the nth delay and forward and see if there is anything there. If there is non-zero terms, then it's infinite impulse response system. All right, so this is again not a competition between good or bad. It's just competition between two kind of different systems. With the finite impulse response systems, actually you can have some nice properties that you cannot achieve by analog filtering, period. With IIR systems, you actually can sacrifice the phase response to get, say, better performance. All right. IIR requires feedback. But if you have a feedback, it doesn't guarantee it's IIR. Just like our recursive 4-point running average. It has a feedback, but it's still finite impulse response system. Any system has only one single impulse response. And for the 4-point running average, this is the impulse response. Definitely a finite. Even though you can also have on the implementation, you have the feedback. So, okay. Yeah. So, if you have a linear time invert system, then the impulse response actually, the transfer function is same as the impulse, this Z transform of impulse response. Wow. All right. So basically the same stuff what I already have. Alrighty. Zeros and poles. Again, back to the zero pole plot. Two cases. Finite impulse response and then infinite impulse response system. They have a difference. For finite impulse response systems, all the poles must be at origo, n poles, or have a pole with canceling zero. The zeros can be anywhere. The finite impulse response system, all the poles are exactly zero, or it has the canceling pole, zero pole pair. For infinite impulse response system, you have at least one pole, between 0 and the unit circle, or actually non-zero pole, which makes it immediately infinite impulse response system unless there is a canceling pole. Canceling zero. Getting mixed up. So basically, the zero pole plot is quite informative actually. It shows you how many zeros and poles the system have, meaning their degree of the system, order number of the system. Then it also shows if it's a finite or infinite impulse response system. Although impulse response, when you feed a delta inside of just any system, then that's by the definition, that's your impulse response. But if you know that the system is LTI, meaning it has a meaningful difference equation, then you can take a look at the zero pole plot and see stability, if the poles are inside of the unit circle, and also if it's FIR or IIR. Okay, one minor thing about these infinite impulse response systems. Basically, almost all natural systems are this type. For example, RC filters or the Salenki filters on analog systems, they are all infinite impulse response systems. On nuclear physics, you have also finite impulse response systems, but they end up with a Big Bang. But anyways, so yeah, unit step response, not really interesting. So instead of the impulse, you will feed the step, unit step in. What you get out is the unit step response, usually marked by S. What is interesting in here actually, if you have a digital system or sampling system, then you can actually compare this one with, say, theoretical model of the system and to see if it makes sense, if the data is what you're expecting it to be. So you can test a sampling system by feeding square wave in, and then take a look at what happens afterwards. Yeah, arbitrary system response. Okay, can be calculated from the difference equation. So that's also a response of the system, and that's the third time-based response. So we have the unit impulse response, which describes the system. We have the unit steps, which actually it's can be used for testing in real life. And then we have, for example, in acoustics, unit step can be used in acoustics. It's hard to get a snap out of the loudspeaker system, but you can actually run a square wave to loudspeakers. On the other hand, on acoustics, impulse response can be measured. Just like that. That's about, impulse, acoustic impulse. Then basically just record that one and you have the impulse response of the room. Meaning what? Now you can basically move this room into digital world and use that as a filter to your, whatever you are playing. So if you want to know what it sounds like if you are playing music, either directly through the earphones, or if you want to simulate a classroom C219. Now do you know how to do it? You just need to record a snap and use that one as the impulse response and use that to filter your data. I have no idea why you would do that, but anyways. All right, so yeah, good. So that was the time-based responses, basically just one, which is the impulse. More important for your case, at least, would it be nice to actually know the frequency response of the system, since you will be filtering. You will be filtering data or signals or audio signals. So I would guess it would be also nice to analyze your filter design to see if it works as it's supposed to work. And there we have the frequency response definition. Similar to analog, let me put it here, analog world. You have the transfer function H of S. You just replace S as J omega, you get the frequency response of the system. That's on the analog domain, but on discrete time systems, we have, instead of H of S, we have H of Z, that rational polynomial. And basically, we get the transfer frequency response. Now I should be careful, actually, on the markings. Digital frequency is a little bit different from the analog frequency. So basically, we replace Z with the e to j omega. That's the angular frequency for sampled systems, not the physical frequency. Here we have omega is just 2 pi f. But in frequency domain, this omega is unitless. It depends on sampling rate. Okay. Omega actually is the same as 2 pi times physical frequency divided by sampling rate. That's the angle on complex plane. And basically, then to calculate this frequency response, you basically just plug in e to j omega instead of the z. So fundamentally, it looks like this: pk times e to minus j k k times j omega divided by k from 0 to n, ak times e to k times j omega. Now I would like to have a complex calculator like MATLAB. You don't need to calculate. You just need to know what this is, all of this shit is all about. All right. But then things get a little bit more interesting, at least for me. If you take a look at this other form, which has the zeros and poles on it, this product form, you have z minus zk. So you have e to j omega minus zk and e to j omega minus pk. Okay, that's the polynomial. Remember the transfer function, that's the z. Ha! Great. This is just the difference between 2 points in z-plane. Right. Okay, and this is the complex spectrum, meaning that it also includes the phase shift. And it can be actually divided in two terms, meaning the amplitude part, j omega there, and complex angle, actually in here, e to j times theta omega. And this is the amplitude response or magnitude response. MATLAB calls it magnitude response. Meaning, okay, how different terms of frequency are treated. So basically, if we have a low pass filter like this is a band pass. Usually, you try to make that on pass band. The system does not change the magnitude. Unity gain on pass band guarantees that. And then on the stop band, you want as much as possible of attenuation. So this would attenuate only unwanted high frequency components. Okay, amplitude response. Then the other part is phase response. Well, this part, theta omega, is phase response, which has a meaning, which comes later. Okay, magnitude response. Let's take the that part a little bit further, since that actually means that we have B0 over A0, the absolute value of that one, and then product K from 1 to N B, not B. E to J omega minus zk divided by k from 1 to n e to j omega minus pk. Ha! Good. Zero pole plot. Again, so first thing what we can actually look at the zero pole plot was stability. Poles inside of the unit circle, stable. Another one was the FIR, poles at origo or a canceling zero at the same place, then it's FIR, otherwise IIR. Third one, amplitude response. This actually, E to J omega, is a point in unit circle at angle omega. Whoa. So that here is a distance. Let me see, I think it's this next one. No, it's not the next one. Okay. For example, we have these zeros at those places and pole, for example, here, triple pole. Okay, that's the product of the distances from this point to all of these zeros divided by the product of this place to all of the poles. So that actually gives a hint of what the amplitude response would look like. But we can also just use MATLAB to calculate it. The frequency response of 3-point running average system looks like that because, well, you can actually, it comes out like that and do just the some calculus, or you can just look at here. Okay, on physical frequencies, okay, the angle right there is actually pi. So basically, it happens when f is here. F is the same as sampling rate over 2, which is the Nyquist frequency. The highest frequency that can be sampled on that system without aliasing. All right, so it would be normalized frequency here, so that's 1 pi rad. And where we have the 0, which means the distance of that point is exactly here. So distance is 0. Same thing there. Distance is 0. So on these 2 points, the amplitude response goes to 0. But otherwise, you know, on the beginning, amplitude response is 1, goes down, then comes up again and goes down. Good. Oh. Yeah, I have the same thing here. Good. But anyways, when calculating the frequency response, this omega here is the normalized frequency, meaning pi equals to sampling rate over 2. 2 pi is exactly as the sampling rate. Good. And I already described that one. So basically, on running average system like that, we have this e to j omega, and that part is the distance between that point on unit circle to those 0 locations. And that one is okay. Hey, I have a couple of animations. How local minimums and maximums actually affect on the when we are moving zeros and poles? What does it look like in the amplitude response? Let's see, does it work? Animated GIF. Yeah. I'm moving the zeros on unit circle, so basically it just moves the 0 point also in amplitude response. And now I move the pole here, so you get more gain, meaning you are getting closer to the unit circle, so you get gain of signal on those points. We have short distance on denominator, less than 1. Okay, so that's how you get gain. Okay, that's zeros again. Let's see. Okay, and pole goes closer to the unit circle. You are starting getting more gain on 0 frequency, meaning DC term. Then I split this one in 2, I think. Yes, and basically that's the bandpass filter on different frequencies, and frequency is marked exactly in here. Right. Flat response animation, I think. That was a nice bandpass system, but let's see, there's a flat response. Okay, that's how to measure it. I have 3 different zeros here, and I wanted passband flat response. So I have these points here actually similar to what you would have on a Butterworth type of analog filter. It has a flat response. And basically this is just calculating these distances to numerators and distances to the denominator roots. Okay, wow, that works fine. So now we have this powerful zero pole plot, which does actually give you 3 things: Fi or IIR, stable or not, and also the frequency, or actually the amplitude response. Couple of words about the phase response. Phase. Phase response gives the information of how the signal is delaying at different frequencies. So we have the theta of omega. So practically, if we have a system, it's that's supposed to be square. We feed in a sinusoid. Well, this is sample, but anyways, how much does T? On a system with the transfer function, we come out with some amplitude at that frequency multiplied by that same sine of theta, oh, not theta, omega t plus the phase shift, omega times t plus phase shift, theta of omega. Okay, so this phase response is practically just how much the phase of that frequency is delaying on the system. Right, so, okay, few cases. If we have theta omega linear, then actually what happens is that sine of omega times t plus, so this is linear, meaning that k times omega, some constant, well, let's mark it t0 times omega. What happens? We have t0 times omega. We have the sinus of omega times t plus t0. Linear phase shift means constant time delay for all different frequency components. Meaning that if you have 2 different frequencies, then what happens to these on the system? They both get different gain, but they still appear on the same time on the output. Which means, for example, if you are doing a data transfer, you really would like to have this, if you have different frequencies moving the different frequencies representing different parts of the same data. You want the same data to remain coherent, meaning you want to have all the frequency components coming out at the same time. You don't want to have, zeros coming earlier than ones. Okay, or for example, multiple frequency shift keying. Okay, then you have different frequencies for different bits on byte, for example. And then you want to have that one byte coherent when it comes out. You don't basically allow any time difference between those different channels. So this is a good property for communication. And the only way you get this one is to have a FIR system. Only symmetric FIR system have linear phase shift. Okay. Non-linear, well, it's also, well, for example, in acoustics, it doesn't really make any difference. Not much at least. As soon as as long as the time shift is not, say, more than 10 milliseconds, which is the amount of the time that people start to recognize the time shift of different channels. Okay, so basically on acoustics or the audio signal processing, then you can use IIR. It gives you more performance, better performance. But anyway, so phase response, symmetric H of n, and these are used on communication filters. Group delay. How to actually measure how many time steps these different frequency components are shifting. Then there's a group delay, which is simply group delay. The theta is simply the phase shift derived by omega. So this is just a derivative. Group delay actually tells you exactly in time. That would be linear phase shift not time here. That's the frequency. And then we have the constant. What is the constant? T0. Okay, T0. Linear phase shift. But if you have a group delay, then it actually non-linear. It usually shows something like that. On passband, so basically this one tells you how many milliseconds or seconds later different components actually are coming out compared to each others. So what is the time delay of a signal at different frequencies to pass through the system. Okay, couple of examples. Input signal as a step, and then the second one has a system with a linear phase shift of linear phase response, meaning this basically comes out symmetric. I told you about only symmetric FIR systems have a linear phase shift. Okay, if you are making a convolution of input signal with the system, the impulse response, and the impulse response is symmetric, it means that both of these edges actually have similar features, so this output is also symmetric on this case. Nonlinear phase shift actually treats the rising edge differently from the falling edge. This is not symmetric anymore. Well, overshoot for this rising edge, and then it has the undershoot on the falling edge. Not symmetric anymore, meaning it has non-constant time delay. Zero phase response. That's a nice trick you can do not on real time but afterwards. Meaning that if you have a IIR system with ugly group delay, just run the signal first through the system and then reverse the time, which you can do, of course. It's your data, do whatever you please. Run the same signal through the same system again, and voila, you have a no phase shift at all. But it doesn't work with the real-time systems. But post-processing, yes, that's a dirty trick that scientists do, and engineers too. All right, good. So we had a frequency response, which is divided in amplitude response and phase response. Phase response basically means how much is the time delay through the system. Okay, in here is 0, and then spectrum analysis of the signals. How to do the spectrum analysis? That's simple. You have done the math already. Spectrum analysis of the signals. Signal spectrum. Simple. So power spectrum of signal is simply Fourier transform of the signal multiplied by the complex conjugate. So it's basically this. This is the power, where the F here is the Fourier transformation. And for discrete time signals, you have the discrete Fourier transform. Practically, depending on the size of the samples, if you have 2 power of n samples, then you can use the fast Fourier transformation. which is the fastest way of calculating the discrete Fourier transform. There's absolutely no magic out of that one. You just do the calculation and it gives you the answer. And yes, there's also a formula for that one, but I'll let the mathematicians to do the formulas. We are using that as a tool. All right. So did I yesterday already show that one? Okay. That's the spectrum analysis of digital sample of where the sampling rate is 1 kilohertz and we have 50 hertz signal and we get this envelope. That envelope comes from the fact that we cannot hide from the math. Math is the only absolute science in the world. Engineering is very close to physics or the other way around. So basically both are based on, say, evidence from the nature. Math is just a tool. So on that example, the signal of, if we are sampling a signal of sine of 2 pi f sig time n times ts, how to basically take only that much of the signal. Mathematics thinks that all the signals what we have are basically from infinity to, or minus infinity to infinity. Okay. So for mathematics, this goes on both sides. But engineers are interested only on some part of it. For example, that part that will be Fourier transform and the power series. You have the multiplication in time is the same as convolution in frequency. We still have this one power peak exactly at f sig mathematically, but we also have the Fourier transform of that one, which is, well, it looks like more or less like that. On the other hand, only these high and low points are showing up. Okay, you can do the math if you want to. I don't mind. When you convolute these together, meaning the Fourier transform of the sine and convolution with Fourier transform of that box, and take the norm out of it, you will end up having those envelopes. Just like that one. Okay. Spectrogram. Spectrogram is a basically a spectrum of signal and how it changes by time. So we have this sample which is longer than that, and we are interested on how that does that one change by time. So what we can spectrogram. Okay. We can calculate the spectrum and put it on frequency axis, on y-axis would be frequency. We will put that spectrum here, so it looks like that one. Then we can calculate with some time step. Say, calculate starting from here, the same thing, to next point. And maybe that spectrum has changed. Okay, and so on. And what we can do is do a time series and images, not just, you know, dull the graphs, but we can actually highlight the those parts which has the highest points and show them on this kind of graph. So this one shows a time series of spectra of subsample data, and this is for chirp signal, meaning that frequency of the signal is changing by time linearly, starting from 0 in this case up to 500 Hertz or so in about 2 seconds. So basically it goes something like that. Yeah, that was full. How about having a break right now? Half an hour or 40 minutes or 45 minutes. It could be a lunch break. Yeah, lunch break. 30 minutes. Is that enough? Okay, let's try to do it in 30 minutes. Good. Lunch break.